Today I will show you a visual study of turbulent shockwave boundary layer interactions. All visualizations are obtained from experimental data in our high-speed wind tunnel at TU Berlin at Mach 2. In textbook gas dynamics, whenever a shock intersects a wall, it gets reflected in such a way so that the flow stays parallel to the surface. Over this reflection, the Mach number decreases and the pressure increases. In reality, the presence of a boundary layer greatly increases the complexity of the flow field. The positive pressure gradient imposed by the shock thickens the boundary layer and, if sufficiently strong, causes it to separate. Over the separation, the flow is deflected, which leads to the formation of a separation shock, expansion waves at the maximum height of the bubble, and compression waves that merge into another reattachment shock at the reattachment point. This kind of interaction is called a closed interaction due to the enclosed separation bubble. It can be described with a separation length that is primarily a function of the incoming shock strength. In addition to the nominally 2D closed interaction on the wind tunnel floor, the full-span shock generator creates a 3D sharp-fin open interaction on the wind tunnel sidewall. This interaction is characterized by a conical symmetry and the so-called upstream influence that causes the streamlines to change direction before the primary shock is reached. When using measurement techniques that integrate over the span of the tunnel, such as Schlieren images, traces of both interactions can be detected. The dominant flow features are from the 2D interaction, but the upstream influence of the 3D interaction can also clearly be seen. Up to this point, we have only considered the spatial variations in the flow field, but one of the most interesting and challenging properties of any shock boundary layer interaction is its inherent unsteadiness over a very wide frequency range. Upstream of the interaction, the supersonic turbulent boundary layer has a very high frequency signature with small-scale structures corresponding to frequencies way above 50 kHz. At the interaction onset, the dominating source of unsteadiness is the separation shock that has a very low frequency, high amplitude signature of around 2 decades lower than the incoming flow. This strong oscillation causes the most trouble when designing high-speed vehicles, since it can induce vibrations and lead to increased stress due to temperature and pressure fluctuations. Further downstream, the shear layer between the separation bubble and the free stream acts as another source of unsteadiness with a frequency peak around 10 kHz. All these features combined make shockwave boundary layer interactions a very challenging but interesting topic of research, and I hope now you can understand a little bit better why. Thank you for your attention, and if you would like to know more, my full presentation will be on Friday afternoon in session FD51.